Yo, what's up? It's your boy, Mr. Oldridge, coming at you with another banger. What we have today is live, well, not live, video. You've got a live breakdown of a titration happening. Now, this video is from a company that's trying to sell you the stuff that you can use to do a titration in the classroom. This guy, I'm going to talk over him because he's not the most exciting man, but that's okay. What he's got here, I'm going to turn on my annotations. What he's got here is called a burette. Now, his is made of plastic, and the ones we have here at the school are made of glass, but they are built the same way. They have all these little demarcations that tell you how many milliliters of fluid is inside. And what you're going to do if you were doing a titration is to take a look at the milliliters that you started with and then subtract the milliliters you end with. Obviously, the difference is the amount that you've added to the beaker down here. Now, this stuff is called the titrant, and you're going to add it to another solution down here. Usually, you don't know the concentration of this solution. What he has, I believe he has HCl, or hydrochloric acid, in this burette. And then down here, he has some NaOH. Now, NaOH is a strong base. So when you take a look at the pH of this, it's going to be very high. HCl is an acid which will help to neutralize that strong base. So the pH will start high. You can expect it to neutralize down to 7. And then if you keep adding acid, there's no more base to neutralize. So you can expect that it could even become acidic if you kept adding the HCl. I'm going to clear what I have here and fast forward through this guy. So he's going on and on about all the equipment that he's got. He's got some special software. He's actually even got something called a drop counter. He's calibrated it to the size of drops to expect out of this stopcock. And that way he can just count the number of drops and know exactly how many milliliters he's put in. That thing is expensive. Anyways, he is going to turn it on so that something is dripping inside. He's got a magnetic stir bar to make sure it's fully mixed all the time. And as we expected, the pH, the y-axis here is measuring pH, is about, I don't know, somewhere between 11 and 12. We could calculate what the concentration of the NaOH is from that, but we're not doing that right now. I just want to point out that he's adding HCl, and actually it looks to me like the pH is staying about the same. Why would that be the case? That's the case because pH is a logarithmic scale. So you have to neutralize 90% of it to get a 1 unit change in pH. Oh, here we go. Now the pH is finally dropping. He's excited. You can tell. I just want to make sure that you can see this graph. Okay, so what that means, or what I'm going to try to get at here, is that it takes you neutralizing 90% of the NaOH to make the pH change by 1. But then to make it change by another 1, you only need to titrate 90% of what's left, which is only 9% of what you started with. And it keeps getting exponentially, the amount that you need to make a pH change of 1 gets exponentially smaller each time. Eventually, you get to a point where you've added the exact same amount of acid as base. I'm talking about the number of H pluses and the number of OH minuses. That point is called the equivalence point. It means you've added equal numbers of moles of H plus compared with OH minus. The equivalence point of a strong acid and strong base is going to lead you to a pH of 7. So you can see the equivalence point is probably somewhere in here. I mean, here on the y-axis, when you've got a pH meter, you can measure it exactly. He's got even more advanced tools that he can use to make that happen. He's going to keep adding some acid. As soon as you've neutralized all the base, the pH goes below 7, and he's done with that. You can see that the pH of the final solution ends up being closer to 2 because he just kept adding HCl, even though all the NaOH had already disappeared. So that is a classic strong acid, strong base titration curve. He obviously started with base, started at the high pH, went almost vertical through the equivalence point, and then it flattened out. because he's just becoming more acidic. He's actually got some fancy tools here. He can do the second derivative on that and then use the x-intercept to find where the equivalence point was. You can see it's close to a pH of 7. Well, he fast forwarded through that. There's your x-intercept. pH is about 7. That's gold. A strong acid, strong base titration should neutralize each other to make a pH of 7 at the equivalence point. Now, when you're doing this in an actual lab, often you're going to maybe not have a pH meter handy. So what you do is you add an indicator. I've got a second video here where they're doing something similar to that. Let's fast forward through this ad. So he's got basically the same setup. He's got his burette. He's got something that he's titrating down here. He's got his magnetic stirrer. But what he has in addition is a little bit of phenolphthalein, an indicator inside of that solution. So he's just going to plug in his stuff. They're going to collect the data, blah, blah, blah. Let's get that titration curve coming up. Okay, so he's adding drops from the stopcock and burette through his drop counter, which is what's going to cause this data to appear here. I want you to look at the solution. As he adds drops, you're going to start to see pink. Now he is starting with acid and he's adding base. The indicator that he's got in there is clear when it's in acid and then turns pink when it's in base. There's a specific pH where that happens, but we've already seen the equivalence point goes almost vertical. It jumps like 5 pH units in there. So I want you to watch this as the drops get added and notice that it starts to turn pink. He's speeding it up time-wise. There we go. You can kind of start to see some pink appearing in that solution. Now, what's happening is the magnetic stir bar is mixing it up. That base that he added, which is hyper concentrated right there because that's where the drop went, gets mixed together. Overall, the solution's still acidic, so it stays clear. All right, drop, 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 drop. You can see it's starting to stay pink just a little bit longer. Your job as a chemist when you're doing a titration is to finish it off and stop right when it turns the faintest amount of pink that actually stays. Because the faintest amount of pink means you have the tiniest amount of base left over from that one extra drop. Drip, 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 drip. Okay, he's gone overboard because he has logging software that can just do all those calculations for him. But as soon as you see that it is faint pink and it stays that way for like 30 seconds, you can be assured that you're at or near the equivalence point. That's when you take a look at how many milliliters of stuff you've used up, and that if you know the concentration of it and you know the volume of the stuff that you added, that tells you the number of moles in this case of base. And then if you know the volume of acid you used here, you can know the concentration of the original solution. Anyways, drip, drip, drip. He's gone way overboard. He started at a very acidic pH. It's blasted through the equivalence point, and he's now solidly in base territory. His pH is above 10. That's wild. Don't drink that. He's pretty impressed with himself. I think they're probably going to do it. No, they're just going to emphasize that this is also a nice titration curve. You're starting with a strong acid. You neutralize it and blast through the pH of 7, where we expect the equivalence point to be. You, as a chemist, would stop at probably about here, just past the equivalence point at what we call the end point. The end point ends up being different from the equivalence point because you're waiting for the pink color to stay. So you've actually added a fraction or one whole drop more than you probably needed to actually neutralize the solution. In addition, I think phenolphthalein changes its pH or changes its color at like 8, which isn't exactly the pH that you want the indicator to change color in a strong acid, strong base titration, but it's good enough. Anyways, start with the acid, go through the equivalence point. If you add even more base, you obviously have a more basic solution. And there you go. That's a beautiful looking titration curve in the opposite direction. starting with an acid and ending with a base. Thanks for being with me. Take care and best of luck.